Hi, I'm Mingyu from Shanghai University. I am very glad to present our work, Zero-Chain Object Transmission for Distributed Big Data Analytics. This work is done by me, Shuaiwei, Wang, Haibo, Chen, and Binyu, Zang. The distributed big data analytics are widely used in many areas. They can hide messy details on distributed data processing, such as task scheduling, resource management, fault tolerance, and so on. Popular big data analytics frameworks include Apache Spark, Flink, and Hadoop. Those frameworks can make programming much easier, so programmers can focus on business logic on data processing. Most frameworks are written in languages like Java and Scala to leverage their rich functionality and reliability. They also rely on the runtime environment provided by the language virtual machines, the Java virtual machine, or JVMs. The workflow of big data processing is like that. First, we will launch managers and workers on various machines. Taking Spark as an example, suppose we want to launch one manager and 3 workers. We will launch them on 4 different machines. So the first step would be users uploading their applications to the Spark manager. The application is uploaded in a Jar format, which contains the Java class files, which will be needed to execute on workers and managers. Once the manager finishes processing the jar file, it will send tasks into 2 different workers so that they can be parallel executed. During the execution, the workers may need to access data generated by other workers. So Spark will initiate the shuffling phase, which means that each worker will fetch data from other workers. After finishing all the processing, the workers will send the results back to the manager. As we can see, in the data processing phase, all nodes actually frequently communicate with each other. The worker communicates with other workers in the shuffling phase, while at the beginning and the end, the manager should communicate with all workers. The communication can be costly, and it becomes even worse for the JVM scenario. This is because each JVM has its own way to represent Java objects, which can be divided into 2 parts. The first part is header part, which stores metadata for each object. And the most important thing is to store an address to the object's type information. It is called a class in OpenJDK. The second part is data, which can store references to other objects. The reference is encoded as absolute virtual address of other objects. Both header and data are different in different JVMs. So if we move an object to JVM1 to JVM2, the object cannot be directly accessed because the class are different and the objects are different, and the JVM do not know how to interpret those fields and methods. To solve this problem, Java has introduced an extra phase called serialization and deserialization, or SMD. The serialization phase converts objects into byte stream, which contains objects data and class information. The byte stream is in a general format agreed by all JVMs. As for deserialization, the byte stream will be converted back to objects so that the receiver can reuse those objects again. The SD phase is quite costly. For the serialization phase, it traverses all reachable objects and packs them, including their type information, into byte arrays. For deserialization, it needs to decode bytes and allocate new object, store the decoded contents. Both serialization and deserialization are compute intensive, and they cannot be improved by better network. What's worse, when the network bandwidth improves, the network transmission time can be reduced, but the serialization and deserialization will become a severe bottleneck. In our evaluation, the SD phase can account for more than a half of the execution time for Spark applications. We also have some existing SD optimizations to improve the performance of SD. Cryo is an open source SD tool which improves the original Java built-in tool. It has optimized the layout of bytecode streams to make it more compact. It can reduce the number of bytes transmitted. However, the transformation phases still exist, which means that the Java object is still needed to transmit in byte stream and transform back to objects later. Shuaiwei is an optimization on SD. Instead of sending binary format it directly sends object graphs. To achieve this, it encodes and decodes type information and references during the SD phase. It can simplify the transformation part, but it still requires transformation on references and type information. Nails is another optimization. It's more RDMA friendly, which means that it can use the RDMA write to directly write object into the receiver machine. However, it still needs references and type informations fixed before using by the receiver. Although existing optimizations can improve the performance of SD, it still requires the transformation between the sender and the receiver. So our question is that, can we totally remove all the SD-related transformation to further improve the performance of serialization and deserialization? So our solution is called ZCOT. It is zero change object transmission, which means that when a receiver receives objects, they can be directly used without any change. With our ZCOT mechanism, the object can be directly read and written. As the figure shows, when a sender wants to send an object, it can directly write an object into a given address. Afterwards, the receiver can directly read the object on the same address without any change. So, how to achieve ZCOT mechanism? First, we require that each JVM has a shared space. We call it exchange space. It is only used for communications among JVMs. Since the exchange space is shared by different JVMs, and all JVMs share the same view on the exchange space, the objects can be directly accessed without pointer fixing when they are stored in the exchange space. Of course, we also use a per JVM private space, so it can be used for normal allocation when applications does not need communication with other JVMs. Now the exchange space can solve the reference fixing problem. But what about class pointers in the header? To solve this problem, the exchange space should contain a class subspace, which stores type information used by all objects in the exchange space. So, when an object is stored into the exchange space, or the object subspace in the figure, no class pointer is required to fix, because all class are stored in the class subspace. The basic idea of ZCOT might be straightforward, but it is not very easy to realize ZCOT. Here we list some challenges. The first one is how to construct a shared space for all JVMs. Second is how to remain compatible with existing applications like Spark. Third is how to manage memory resources among JVMs, especially in a distributed environment. To construct a space shared by multiple JVMs, we use a mechanism called DCDS, or Distributed Class Data Sharing. It actually extends the built-in application class data sharing mechanism in OpenJDK to support distributed sharing in both class and objects. First, we generate a class archive from user Jiao through the AppCDS tools provided by OpenJDK community. Secondly, we distribute the class archive into different JVMs. The class archive actually contains all classes which will be used in communication later. Thirdly, when the JVMs are launched, they will map the class archive into the same address and construct the class subspace and the object subspace. So from now on, we will generate a shared exchange space for all JVMs on the same virtual address. So the second challenge is the compatibility with existing applications. We have known that ZCOT sends and receives our data in an object format. However, existing applications like Spark and Flink still use SMD interfaces. Serialization use interfaces like write objects, which writes objects into a byte output stream. Deserialization uses read object, which reads from a byte input stream and converts them to an object. So this problem is that how to remain compatible with ZCOT's object-based mechanism. To resolve the compatibility problem, ZCOT's solution is two-level data transmission, which means that ZCOT's transmission is divided into front-end and back-end. In the front-end, ZCOT tries to remain compatible with original SD interfaces. Suppose we want to copy an object whose start address is 0x3000. We still use the output stream and input stream to transmit byte buffers, but the data is actually some simple metadata. In this example, we store the start address and the whole length of the objects into the output stream. It will be sent to the receiver via the input stream. Meanwhile, the backend actually sends and receives real objects. ZCOT will allocate send buffer and receive buffer for the sender and receiver, and they will be used to send data through different JVMs, whose length is equal to the metadata in the front-end sending. Now, the third challenge is manage memory in a distributed environment. ZCOT uses a metadata server to manage the exchange space. The basic unit for management is chunk. Since ZCOT is mainly designed for big data analytics, the default size is quite large. It's 256 megabytes. ZCOT further uses an allocation map, which marks if a chunk has been allocated for each bit. ZCOT also uses a chunk mapping table to mark which JVMs has a copy of a chunk. In the example, it shows that the chunk 1 is copied by the JVM 1 and the chunk 4 is copied by JVM 0. ZCOT also needs to maintain a member table, which contains information for all Java virtual machines. In the member table, we can find the IP and the port of different JVMs. They can be used to maintain network communications and connections between different JVMs. Upon the data structure, the metadata server provides 4 RPC interfaces for JVMs. The first one is register, which is used to register JVM into the member table. It is usually used when a JVM is launched. The second one is acquire, which acquire a new chunk from the metadata server. The third one is get remote, which gets a remote chunk from other JVMs. Although other JVMs actually contain copies for different chunks, it still needs coordination from the metadata server, so we provide this RPC. The fourth one is release, which releases a chunk to the metadata server when it's no longer used. Since RPC interfaces manage the memory in distributed environment, it needs to be integrated with memory management of individual JVMs. For example, the garbage collection of a JVM should invoke the release RPC when it finds that all objects in a chunk is no longer reachable. Now we have introduced the challenges of ZCOT and how to resolve them. We will use an example to show how ZCOT works with a sender and a receiver. We can see that both the sender and receiver has a private space for normal allocation, and they share the same view on the exchange space. Meanwhile, there are also a metadata server to serve the distributed allocation for sender and receiver. Suppose the sender wants to send an object. It will first acquire chunks from the metadata server through the acquire API. When the metadata server receives the acquire API, it will first allocate a chunk. Suppose the chunk's address is 0x10,000. Afterwards, it will maintain the chunk mapping table to mark that JVM1 owns the chunk 1, whose address is 0x10,000. When receiving the chunk, the sender will copy an object from the private space to exchange space, whose address is given by response. After copying, it will also maintain the metadata, including the start address and the length of objects. Afterward, the sender will send the metadata through the output stream and input stream via the front-end sending. Now the receiver will receive the metadata and use it later. Since the metadata in the front-end sending has contained the start address of an object, the receiver now can access the objects at a given address. However, since the real data is not transmitted yet, the access will cause a page fault on the receiver side. When a page fault is triggered, the receiver will go into a pre-registered page fault handler, which sends a get remote RPC to the metadata server. The metadata server will find that the given address is chunk 1, and the JVM1 has a copy of chunk 1. So it forwards the RPC to the sender, actually the JVM1. Finally, JVM1, the sender, will send the chunk 1 to the receiver at the given address. Now the receiver can directly access those objects and without any changing. Now we have introduced the basic workflow of the ZCOT, but we actually discuss many details in our paper. For example, we discuss how data should be persisted if the application requires. We also discuss group-based prefetching so that we can reduce the number of page faults and reduce the overhead. We also discuss how to integrate ZCOT with GC so that the GC overhead will be large. We also find that the data transmitted in different rounds may be duplicated and implement a data duplication optimization. For all those details, please check our paper. As for evaluation, we use a cluster with 4 nodes for evaluation. It contains 100 gigabits network cards, and each node contains 2 CPUs and 128 gigabytes DRAM. And for the evaluation, we use 3 different evaluations. The first one is Mircobenchmark, and the other 2 are Spark and Flink. The Mircobenchmark uses the microperf tester from Nelt for evaluation. The microperf serialize and deserialize different kinds of data structure and send them through network and evaluate performance. Since it only contains some simple data structure, we use a data structure called media files from the Shuaiwei to test its performance. We evaluate ZCOT against 4 aforementioned baselines: the Java built-in serializer or JSL, CRYL, Shuaiwei, and else. The performance shows that ZCOT can improve transmission phases against all baselines. The average improvement compared with NELS is 2.28 times. As for Spark, we first find that it is easy to integrate the ZCOT into Spark's codebase. Since ZCOT is compatible with Spark's SD interface, we only need to implement a ZC serializer in place of the original CRYL serializer and the Java serializer, and configure the Spark to use ZC serializer instead of others. The number of codes of ZC serializer is only 70. And for evaluation results, we find that application execution time can be improved by 13.9% average on 5 applications against CRYL, which is the default serializer in Spark. We have broken down the application time, and we find that in the right part, which contains the serialization phase, ZCOT can reach 4.19 times speed up compared with CRYL. And for the read part, the speed up is 2.95 times. And for Flink's performance, we evaluated with 4 different queries in TPC-H. We can find that ZCOT can receive 22.2% improvement at best in a query 10. Actually, the improvement is less compared with Spark. This is because the Flink SD interfaces and the libraries is manually optimized. However, even those are manually optimized, ZCOT can still receive some improvement. Okay, to conclude, the data transmission phase is actually very costly in big data analytics, especially in distributed environments. The scenario becomes more severe in Java because of the extra serialization and the deserialization phase, or SD. In this work, we propose ZCOT, zero change object transmission, which sends and receives objects through a shared exchange space. When a receiver receives objects, it can directly use them without any transformation and changing. Besides, ZCOT also remains compatible with existing SD interfaces. The evaluation shows that ZCOT can receive significant speed up against SD libraries and existing optimizations. Thank you for listening, and I'm ready to take questions.